All right, so this is going to be the last lesson in the unit. Um, and essentially what we're going to do is we're going to mess around with complex numbers in polar form. So if you're not sure what that means, there was a lesson before this. You can go check that out. But I want to talk more about this idea of the polar form of a complex number real quick before we get into all the algebra stuff of everything. So real quick, I made one up: -6 plus 6 rad 3I. So if you're not sure where that is, right, remember in the complex plane, this is your real, whoops, and this is your imaginary. And so -6 to the left and then up, so we're in quadrant 2, and you would have this guy there, right? So well, I guess the point would just be there. But if we want to know the radius, or we called it the modulus, we needed to know that. And we also needed to know the angle, right? So we needed r, and we needed theta. So the radius, we said, is found by doing, right, the square root of, and so -6 squared plus 6 rad 3 squared, okay? And so I don't know, what's 36 times 3? Oh, that's going to be tough. 36 times 3, don't want to beat me to it, is that 108? 36 times 3. The iPhone says 108. So R equals 36 plus 108. What do we think? What do we think? What do we think? I probably should have known that it was going to be 12, huh? Whoopsie. All right, so anyway, 12. Okay, and then theta is found by using tangent, right? So tangent of theta equals y over x, or 6 rad 3 over -6. So we have tangent of theta equals -rad 3, but I'm going to pick one in quadrant 2 because that's where we need to be. And so tangent being -rad 3 in quadrant 2, I'm going to hit you with a 2 pi thirds. Feeling a little rusty on my trig stuff, but I think we got it. Okay, so then here is the complex number. We said you could write it as z equals, right, 12, and then times the cosine first. Sorry. Cosine of theta plus I sine of theta. Oh, geez. We actually have theta. I got to put that in there. Silly goose. 2 pi thirds. 2 pi thirds. Done. So there it is. All right, so that's the polar form of a complex number as we talked about it last. So there's this other way of writing um, this complex number in polar form. So just there's an exponential form, and I just want to say of polar form, right? So we're still talking polar form. We're still using the same radius and the same angle of this guy. So essentially I'm saying -6 plus 6 rad 3 I could have been written, instead of this guy up there, I'm going to use this. So we could have said z equals, and it would have been 12 e to the 2 pi thirds I. And you can literally plug that into a calculator, right? So like if you take one of our calculators, the TI Inspires, and you do like 12 and then e raised to the 2 pi thirds I, it'll actually, like, when you hit enter, it'll pump out that guy right there. Like, it'll be done. So kind of wild. So it's just another way, and it gets used quite a bit in like algebraic settings, like we'll do today, because the math is just significantly easier than if you're doing it with this form, right? This form is fine, and there's nothing wrong with it. It just can make math a little more tedious. When you're using the exponential form, you can use properties of exponents, which we're going to do, and it makes life significantly easier, and you're not having to memorize new forms and formulas and theorems and stuff. You just are like, well, I know properties of exponents. So I'll just use exponential form, and that's kind of how I'm going to teach this lesson. But you can write any number in exponential form because every number is a complex number or falls under the complex number set. So like here's a fun one. The number 1 can be written in polar form of a complex number. So if you think you're like, wait, what are you talking about? The number 1. Okay, so the graph, right, would just be here, that point right there, the number 1, the real part. There's no imaginary part. So that's where it is, right? Real, imaginary. And so how could you write this? Well, the radius is just 1. So r would be 1. And what's the angle? Well, look at where the angle is, right? You have it at 0. So you could say z equals r, which is 1, and then e to the 0 I. And when you think about it, it's like, well, what's 0 times I? It'd be 0. And what's e to the 0? It'd be 1. And so the number 1 could be e to the 0 I. The number -1 is always a fun one because it gets used a bunch, right? So there's a -1 would be right here on the real axis. And you say, okay, well, what's the radius? The radius is still 1, right? So it'd be 1. And then e, and then what's the angle? Well, the angle goes like that, so that'd be pi. So e to the pi I is -1. Once again, this could also have been written z equals 1 for the radius, and then cosine of theta, or excuse me, not cosine of theta, cosine of pi plus I sine of pi. This would have achieved the same number, -1. It's just two different ways of writing it. Okay, so you have your exponential form, and then you just have your regular form of that. So let's try this one more time. Let's make one up. We'll go with 2 minus 2 I. Okay, so 2 minus 2I. So if you're thinking, okay, where is that? That's in quadrant 4, right? And so then the radius, if you're good with your triangles, the radius would be 2 rad 2. And theta is going to be one of the fourths, but we're in quadrant 4, so we'll say 7 pi fourths. So what I'm saying is that instead of doing the long one, you could do the short exponential form, which would be z equals 2 rad 2, right, e to the 7 pi fourths I. And boom, it's nice, it's done. So it makes life a little bit funner. Look at this, it's 12:26 a.m. on Cinco de Mayo. What's up, I guess, on a Taco Tuesday. Look at that. Oh, might have to hit it up. Too bad everything's closed. Anyway, so, you can write it that way. All right. So, what are we going to do? Today, we're going to talk about this guy, Demois. He has this theorem with exponents, which will be fun. We're going to use that a couple times. But then also, we're just going to mess around algebraically with complex numbers in their polar form. Okay. So before we get to Demois' theorem, let's just talk about multiplying and dividing in polar forms. All right. So I've got two polar form numbers here, right? So I've got the first one with a radius of 2 and theta is pi fourths, and then the second one, radius of 5 and theta is pi thirds. Okay. What we're going to do is in A, we're going to multiply them, and in B, we're going to divide them. So if you think to yourself, like, what would I even do? You can hit pause and try it out. It's really not that hard. But what would I do if I had to multiply all of this, right? Which would not be the end of the world, let's be honest. People have done it. It's doable. If I had to multiply all of this, right, in green highlighted, times all the other green stuff, or what if I had to divide them? Okay, so how would you do that? Well, I think it would be better if you use the exponential form because anybody who's watching this video, if I ask you what do you do when you multiply like bases together, you would say add the exponents. And if I said what do you do when you divide them, you would say subtract the exponents. So we're going to use that as our guide. So here we go. Z1 in exponential form. First thing we're going to do is write in exponential form. If you left it in the highlighted stuff, you would have to use formulas that we learned about in the last unit. And if you don't remember the formulas, then obviously that'll prove tricky. But if you remember the formulas, it's a lot of algebra, but it gets the job done. So I say write an exponential form because I think for time's sake, you want to be done with this class quick. I feel like we're all at that point. Anyway, much love, but whatever. Here we go, 2, and then 2, and then e to the pi fourth I, and z2 would be 5e to the pi thirds I. Okay, and so if I'm going to multiply them, and literally, I know this is like not the best instruction, but literally just like do good math. You're like, what do you mean? I mean, like literally do good math. Like take 2e to the pi fourth I and multiply by 5e to the pi thirds I. And to be honest, if you knew nothing about polar, you should still be able to multiply these together. Like if you saw this on just some random standardized test, you should be able to say to yourself, okay, well, 2 times 5 is 10. E to the pi fourth I times e to the pi thirds I should add the exponent. So e to the pi fourth, and I'm going to write this a little bit differently, plus pi thirds. I'm just going to factor out the I because we don't really like need to have written twice. Save some ink. So anyway, pi fourths plus pi thirds. Now comes the tough math. Pi fourths plus pi thirds. That's 3 over 12 plus 4 over 12, which makes 7 over 12. So then you write 10 e to the 7 pi over 12 I. And you can leave it as that. Or if somebody's like being a real stickler and you're like, okay, fine, I'll put it back into the normal form, then it would be like 10 and then cosine of 7 pi over 12 plus I sine of 7 pi over 12, like that. And it's really not that bad. So if I was dividing, I would take the 2, right? Like 2e to the pi fourth I over 5e to the pi thirds I. And then when you divide, what do you do with the exponents? You subtract. So I'd say 2/5 e, and then we're going to do pi fourths, right? Numerator minus denominator is how you do that. Minus pi thirds I. What did I just say that was? I said that was 3/12 minus 4/12. Is that what I was at? 3/12 minus 4/12. So that would be negative 1/12. So 2/4 or 2/5 e to the negative pi 12 I. And once again, you can leave it as that, or if somebody's like, no, write it this way, then you can. I really like this way, to be honest. But it'd be 2/5 and then cosine of negative pi 12 plus I sine of negative pi 12. Boom, done. So yeah, so I guess just to kind of wrap this up, if you're having to do like some algebra with polar form of complex numbers, I would tell you don't try to make it hard on yourself and leave it in these forms. Make life better and put it into exponential form, and then just do good math. And I think you'll find that the work is pretty straightforward and not that difficult. Okay, so now on to this guy. This is just saying that if you left the complex number in this polar form, then for any integer n, see, notice n is an exponent. If you raise the complex number to the nth power, then essentially you get this as the result. Now I'll just prove it to you with the polar form and exponential form. So z equals, right, what do we say, r e to the theta I. We say, okay. Now let's raise this to the nth power, right? Z to the n. We would then say you take this whole thing, r, and then e to the theta I, and you raise it to the nth power. So what do you get? You get, well, r to the n. And then what do you do when you have exponents? raised to more exponents, right? So exponents raised to more exponents, you multiply. So then, you get e, and then you multiply. So n times theta I would be z to the n. So then when you're looking at this, okay, well then the radius is now r to the nth, and then e to the n theta I would essentially, this is the part that's going into the sine and cosine n theta, and you see that there. And so once again, exponential form proves better because you learned in Algebra 1 the properties of exponents, and why relearn something like why learn a theorem. I'm not saying that the theorem is bad. I mean, obviously this guy's accomplished a lot. I don't know. He's probably dead, but if he's not, good job, man. Google it. But you know, for the class sake and just getting this done, why not just know properties of exponents? So you just multiply that. So let's see how that works. So take a look. Find the indicated power using De Moivre's theorem. Okay, the answer to that is no, I will not. But I will use some thoughts about it. So first things first, this says 1 minus I to the 8th. If you don't listen to this and do it this way, then what you would have to do is you would have to do 1 minus I times 1 minus I, and you would have to write it out 8 times and then FOIL. So good luck if you're not going to do your homework. So do your homework, right? Pay attention. Check this out. Okay, follow along. Here we go. So first thing I would do is I would take 1 minus I, just this part right here, and you guessed it. I'll take that part and I'm going to write it in exponential form. Okay, so where's that at? That's in quadrant 4. And let's see, what's 1 squared plus 1 squared? That's 2, so square root of 2. So the radius I get is rad 2, and 1 and 1, so it's 45. So theta in quadrant 4 is 7 pi over 4. Okay, so in exponential form, this is going to be, I'm not going to use z, it's just going to be square root of 2 e to the 7 pi over 4 I. Yep, good, great. Now you're raising it to the 8th power, right? So we're going to raise it to whatever exponent's in the problem. Okay, so once again, you raise to the 8th, so we multiply. The square root is 1/2 power, so 1/2 times 8 is 4. So we're going to do 2 to the 4th, and then 7 pi over 4 I times 8. Let's see, the 4 would reduce, so e to the 14 pi I. Does that seem good? Hopefully. So then you get 16, and we're actually going to solve this out. So, because it says like find it, you know what I mean? Like, so find. So this isn't really finding it. Finding it would be probably like going to this 16 cosine of 14 pi plus I sine of 14 pi, and like actually figuring it out. So probably we'll be using some numbers that you could actually do without a calculator. So 14 pi, that's 7 revolutions. That gets all the way back at 2 pi. So cosine would be 1 plus I times 0, which is just 0, right? So then it's just going to be 16. Wild. Look at that, kids. Look at that. Isn't that crazy? New exciting riddle you can give to your parents while in quarantine here. Ask them what 1 minus I to the 8th is. Boom, 16. Okay, let's try another one. So you got 1 minus rad 3I. If you need to draw it out, right? So like here's 1, here's let's say rad 3, boom, right there. And if you need to draw it out so that you can be like, okay, that's 1, that's rad 3. If I square that, 1, 3, 4, so this is 2. That's the radius, right? So the radius is 2. And the angle, you're like, okay, the angle, is where I need to get to. Tangent of theta would equal negative rad 3 over 1, so negative rad 3. So we're at a pi thirds situation, right? Tangent of pi thirds is rad 3, so we're at 5 pi thirds. Okay, and so those would be the two things that we're going to use. So you've got, excuse me, 2, and then e to the 5 pi thirds, I, and then to the 5th power. Okay, and so then we're going to go 2 to the 5th, e to the 25 pi thirds, I. That sounds gross. Okay, and now we're going to actually do it out. So 32 cosine of 25 pi over 3 plus I sine of 25 pi over 3. Okay. 25 pi over 3. What do you think? 24 over 3 would be 8. Do you agree with this? I think you should. Yeah. So 8 pi would be 24 over 3. So that means it goes all the way around 4 times. Does this seem right? Yeah, I'm liking what that's saying. So it goes around 4 times and then an extra pi thirds. So this is really just the same as pi thirds. So cosine of pi thirds is 1/2. And then sine of pi thirds is rad 3 over 2. Now let's multiply it by 32. 16 plus 16 rad 3i. Look at that. Isn't that fun? Okay, so first off, for the kids that do not pay attention, who don't read this, and then they try to take the test this coming week, they're going to try and write this thing out and multiply it all out. I've seen it before. It's the worst. They don't finish the test, and that's sad news for them. Okay, so clearly you don't want to write this out 5 times and then multiply it all together. Sounds terrible. Second, I don't think you want to memorize this either. Whoa. I just don't think you really want to. So why memorize that? Here's what we can do, right? We go exponential form of the complex number, and that's this guy right here. And then we use our understanding of properties of exponents, and then we can bring it back into the form of the complex number and work it out if need be, okay? And it should be good, okay? I think it's easier. I think it works better that way. So give it a shot. Let me know your thoughts. Okay. The last thing we're going to do is we're going to talk about finding roots of complex numbers. So we've done multiplying, we've done dividing, we've done raising it to an exponent. Now we're going to do square roots. So the first thing is we're going to talk nth roots, right? Nth roots. And so remember, n is considered the index. Now, here's the weird thing about roots of complex numbers. Here's the crazy thing. You will get, check it. You will get n answers. So, like if you're on a game show and somebody's like, what's the square root of 4? You're going to be like, oh, the square root of 4 is 2. And that's all you're going to say. And you're going to win the game show and you'll be a hero and it'll be great. But if it's a complex number, right? Somebody's going to say to you, what's the cube root of 4 rad 3 minus 4i? You are going to need to give them 3 answers, right? Because the index of the cube root is 3. So notice the language there says find the cube roots of 4 rad 3 minus 4i. So it gets kind of wild in that respect, okay? So we're going to actually have to find 3 things, but we're going to use what we just did to help us out. All right, so De Moivre's theorem comes into play here with the whole raising things to an exponent. The last thing I'll say about nth roots, remember they can be written as exponents, as 1 over n, right? That's the exponent. So first thing we're going to do is we're going to write this in exponential form. And then after after that, we'll raise, instead of using the radical, we'll just raise it to be 1 over n power. Okay, so we'll use those ideas. So where are we at? We're in quadrant 4 again. Man, you would have thought I picked a different quadrant. Okay, but we did get a different angle, so that's good. So if you're here, right, 4 rad 3 somewhere over here, 4 here, boom. The radius, once again, is still just going to be 8 because it's 30, 60, 90 triangle. Theta, ooh, okay, so tangent of theta would equal -4 over 4 rad 3. What's that going to be? Negative rad 3 over 3? So tangent equaling that, it's going to have to be at 30 degrees or pi 6 scenario. So I'm going to say 11 pi over 6. Okay, this is going to get crazy. All right, so this is, right, z equals 8 e to the 11 pi over 6 I. Okay. And so now we're just going to raise it to the 1/3 power. So 8 e to the 11 pi over 6 I to the 1/3. Okay, okay, okay. So first answer, we are going to call, our textbook just calls it W sub 0 or W naught. Okay, so that would be 8 to the 1/3, which is 2. Cube root of 8 is 2. And then e to the what? 11 pi over 18 I. Okay, that's the first answer. There are 2 more answers. So you got to find all answers, and it's really easy to do. So how do you spell answer? There's a W there. Answers by adding, okay, 2 pi over n to theta. All right, so we got 11 pi over 18. So the next one is called W sub 1. Still going to be 2. Now it's going to be e to the 11 pi over 18. We're going to have to add 2 pi thirds. So we got to get a common denominator. That would be 12 over 18. So, right, this would be times 6 times 6. So that'd be 12 over 18. So 12 plus 11, 23. So 23 pi over 18. And then to find the last one, you do it again. 2e, and then you have to add another 2 pi thirds. And so then 12 over 18 would be 35. Whoops. 35 pi over 18 pi. And the reason you don't do another one is because all it's going to do is circle back around to the first angle. So if you add another 12 pi over 18, you'll just come back to the same angle as 11 pi over 18. So those are the 3 cube roots. So this is your answer right here. And I'm not going to make you write them out. Like, this is good enough for me. Okay. So to find all the cube roots, you just use de Moivre's theorem at the beginning, but just use the 1/3 power. And then from there, to find all the other answers, you add until you have enough. And you should never go over 2 pi. So if you look at all my angles are 11 pi over 18, 23 pi over 18. Oh, I forgot an I. 23 pi over 18 I, and 35 pi over 18 I. If you notice, all 3 angles are under 2 pi. That's how it should be. They should not go over 2 pi. If you go over 2 pi, then you either have too many answers or you messed up. So hopefully that makes sense. All right, so here we go. Then do one. I like this question, and I think I'm just going to wrap it up, but who knows? Maybe I'll do one. But find the 3rd, 4th root of negative 81i. So what I mean by that, 3rd, 4th root. So W sub 0 is the first answer, W sub 1 would be the next, W sub 2 would be the third, and W sub 3 would be the last one, right? So that makes 4 answers. So when I say find the third, fourth root, I mean this one. Okay, so like nice test question, you know, like I don't have to look for all of your work. I just got to look for one thing. So negative 81i, okay, let's graph it. Let's graph it. Let's graph it. Where would negative 81i be on the complex plane? It would be down here, right? So let's talk radius. Radius 81. Let's talk theta, 3 pi over 2. Okay, so I'm going to go 81 e to the 3 pi over 2 I. That would be the complex number in exponential form, and we're going to go with the fourth root, so that's the 1/4 power. So the fourth root of 81 is 3 e, so then we're going to multiply exponents, so 3 pi over 8 I. So this is the first answer, right? 3 e to the 3 pi over 8 I. Now the question is how could I just get to that? Well, what would you add, right? Like each time. So if you go back and look, I said you had to add 2 pi over n. So if n is 4, 2 pi over 4 would be pi over 2. So plus pi over 2, plus pi over 2 to get this answer. So essentially add pi. So what's that? 8 over 8. So this would be 3e to the 11 pi over 8 pi. And that's it. Okay. Found the third one. Okay. But that's it. So the key thing you have to remember is that if we're doing the fourth root, we need 4 answers. The way to find all 4 answers is once you get the first one, then you add 2 pi over n until you complete all the answers. But I really think, hopefully I've proven that it is a good idea to put these things together like that, okay, in exponential form. So this takes a minute, but if you put it all together, okay, in algebra 2, you should have been able to solve this problem, right? Like, so like this problem in algebra 2, or even in this class, I mean, when you're doing polynomials, the degree is 3, you're supposed to get 3 answers, okay, right? You can't just be like z cubed equals 1, and then you cube root, and so you say like z equals 1, and there's no plus or minus because it's a cube root. So, you know, like that's an algebra 1 calling, kind of that problem. Algebra 2, you would have said, oh, I can factor this z minus 1, right? And then z squared plus z plus 1, I think is AB. Yeah. Right? And then you factor. So here's your z equals 1, and then this is the quadratic, so you can get 2 answers, yada, 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 and solve it out. Okay, whether you complete the square or the quadratic formula. What I'm saying is you could actually use a third method now and solve it this way. So z cubed, you go equals 1, but then we're going to write 1 in complex form. So 1 in complex form is e to the 0i. And we're going to call it z cubed. And I know you're sitting there, you're like, why would you do this? Because it's actually easier. Cube root, the z equals, okay? And we would get the cube root of 1 is 1. And then we're raising this to the 1/3. And so we multiply exponents. So it still would be e to the 0i. And like then, so this is z sub 0, z sub 1, z sub 2. And you just have to add 2 pi thirds each time. So it'd be 1 e. And then you got to add 2 pi thirds. So 2 pi thirds I. And then 1 e to the 4 pi thirds I. And I'm not kidding, this is like literally easier. So this goes to just 1. And then 2 pi thirds, cosine of 2 pi thirds is negative 1/2. So we negative 1/2 plus I sine of 2 pi thirds. So what's sine of 2 pi thirds? Positive rad 3 over 2. So rad 3 over 2 I. And then this guy over here, e to the 4 pi thirds I, would be cosine of 4 pi thirds is also negative 1/2. And then the sign is negative rad 3 over 2i. Guys, look at this. It's so easy. Done. I'm telling you. What if you forgot how to complete the square? God forbid you forgot how to complete the square. But, you know, you would have to complete the square with that, get an answer. I mean, it's really not that hard. but you get the same thing. That's crazy. Isn't this crazy? I think from a fun math perspective, it is kind of crazy and cool. And that's kind of the lesson. All right, so gets kind of wild, kind of fun, messing around with complex numbers. Hopefully, it makes sense. Watch it a few times. I know it's kind of long, but wish you all the best and talk to you soon. Don't forget, test's gonna be at the end of the week. Peace out.